Welcome back. In this lecture, we will introduce a term, capacity fade, that you might often hear, especially in the context of lithium-ion battery, but it is a term that is generally applicable to any secondary battery. So the central feature of a secondary battery is that it is rechargeable. So it is typically used for many cycles. So it, this term is best elaborated via the schematic. So this is a capacity fade in a lithium-ion battery. So along the x-axis, we are plotting the number of cycles. Along the y-axis, we have the capacity as indicated in ampere hour. So typically what happens is that as you keep using the battery, the amount of useful capacity keeps decreasing. So you typically do not use the battery once it the capacity becomes less than a particular value. So what is the practical consequence? For example, if you start using the battery in the initial cycles, supposing in your cell phone, the the battery would serve you for about, let's say, 6 hours. So in time, within 4 hours, 3 hours, 2 hours, and so on, you have to keep recharging the battery. Okay, so this is because of capacity fade. So in time, the time to recharge is so frequent, so you just discard the battery, you change the battery. So this is an important feature, and a lot of effort has gone into understanding why capacity fade occurs in many batteries, especially in the context of lithium-ion batteries. This is most well understood in the context of lithium-ion batteries. So this phenomena is associated in the context of lithium-ion batteries with the formation of solid electrolyte interface. We have elaborated what solid electrolyte interface means in a previous lecture. So please refer to this lecture. Um, so what is occurring during capacity fade, or the dominant mechanism, is that the lithium is irreversibly lost when solid electrolyte interface is formed. So typically the solid electrolyte interface formed at the interface between the graphite electrode and electrolyte. This is what is attributed to capacity fade. So as the solid electrolyte interface is formed, in a way, this is an useful feature. That is, the formation of solid electrolyte interface is an useful feature because it suppresses further corrosion at this interface. But while this is being formed, some lithium gets accumulated irreversibly. That is not available for further cycling. See, typically when you have lithium being cycled, that is, the lithium shuttles between one electrode to the other. So that is the reversible movement of lithium. That is the central feature of a secondary battery, but the capacity fade in a lithium ion battery is attributed to lithium that gets stored in the solid electrolyte interface but cannot be retrieved any further and cannot be used for further cycling. So, how do you suppress this capacity fade is one of the frontier research areas. Um, we will not elaborate any further the other mechanisms. So, one of the other feature that is often discussed in the context of capacity fade is the this terminology, depth of discharge. This is the extent to which battery is discharged during cycling. So that's what we refer to by the depth of discharge. So let's look at this particular schematic. So a battery can be discharged to different extent. For example, if you discharge to, let's say, to only 10%, the cycle life is larger. Okay, so but you typically do not want to keep charging the battery often, right? So you, even though you may have greater cycle life, if you keep discharging only to a lesser extent, but that is not really practical. However, if you discharge it, let's say beyond, let's say 70% or close to, let's say 100%, the number of cycles that you may use the battery for decreases. So here, this information is provided for two dominant secondary ion batteries. One is the lithium ion battery, another is the lead acid battery. In both the cases, as you increase the depth of discharge, so if you discharge to a greater extent, the cycle life decreases. The number of cycles for which you may use this battery decreases. So typically, you avoid the either extremes. It's not that you want to be charging too frequently, or you want to be discharging to a great extent. So you typically restrict your depth of discharge to 40 to 70%. This is the typical range in which you um, work, and this is sort of an optimal. And so corresponding to this depth of discharge, the cycle life is indicated here. So this is the concluding lecture for a series of lectures which um, we have provided for covering fundamentals of battery. So where did we start? We started with sort of descriptive lectures, descriptive but yet conceptual and important. So this involved the variety of battery chemistries that have been developed over 100 years, and we classified all the battery chemistries under primary and secondary batteries. Then we also looked at different kinds of electrode. The dominant electrode right now is the insertion electrode, which is utilized in lithium ion battery. But reconstruction electrodes are also important. In my opinion, the central aspect of battery fundamentals is covered via understanding electrochemical thermodynamics and electrochemical kinetics. So these aspects were covered in previous playlist under Introduction to Electrochemical Engineering. So you should refer to lectures on electrochemical thermodynamics and kinetics. And to understand battery fundamentals deeply, you should apply these conceptual issues in the context of batteries. So we have discussed the characteristic of battery via discussion on thermodynamics and kinetics. So you should take time to understand this particular feature. Then we also looked at other features that are of importance: efficiency of batteries, heat generation in batteries. And we looked at a variety of electrochemical energy conversion and storage devices under the Ragone plot. We also addressed features of self-discharge, the different mechanisms that is attributed to self-discharge. And in this lecture, we looked at capacity fade. So battery is an extensive topic you can cover over one semester. So, but this course is about providing an overview of different electrochemical energy conversion and storage devices. So, what is a good place to read more about batteries? Very good source that is often updated periodically is this particular book. Okay, so it serves two purposes. One is that this is provides fairly recent update on different chapters written by leading experts in battery science and technology. So this is a very good source to get a broad overview of batteries, and it also provides important references. As I said, it is written by the leading researchers, so you will get very deep and comprehensive um, understanding. However, if you look at the size of the book, you will also understand it's a surrogate to a visit to a gymnasium. So if you have this book, if you lift this book 50 times, that really helps. So it is mentally and physically very useful. So you should probably take a look at this handbook if you're going to be working on batteries. So this concludes the series of lectures on battery fundamentals, but we will also look at batteries in some other context, in a rather applied context later in this course. Thank you.